Now we've talked about background theory for confidence intervals. Now let's get into some of our nitty-gritty details. So the first one is our confidence level and critical values. Our confidence level is how many of our possible confidence intervals will contain our population parameter. So if you want a 95% confidence level, that means that 95% of all the possible samples would give you confidence intervals that contain the population parameter. So if you wanted to say a 68% confidence level, that would mean that about 68% of all the possible samples would give you confidence intervals that contain the population proportion P. So our confidence level is set by what's called a critical value. That's a value that tells you how many standard errors you have to go to get the correct confidence level. So if you wanted a 68% confidence level, you would have to go about 1 standard error from the estimate. If you wanted a 95% confidence level, you would have to go about 2 standard errors, or if you want to be more precise, 1.96, since we just looked that up. And if you wanted a 99.7% confidence level, you would have to go about 3 standard errors from our estimate. Okay. This is all just based on our empirical rule, which we've used over and over so far. Our confidence level is often written as 1 minus alpha times 100%, where alpha is the combined area from both tails. So if you want a 95%, that means you have 0.95 in the middle. And how much would be in the tails? That means 0.95 in the middle, so 0.05 in the tails. So that means alpha would equal 0.05. So you'd write it as a 95% confidence interval, okay? And you'd say alpha equals 0.05. The sampling distribution for our sample proportions follows a normal curve. So we use the standard normal curve to look up our critical values, which we're going to call Z star. So if you're given the left tail area, you look up Q norm of the area. If you're given the right tail area, we can use Q norm area, comma, lower dot tail equals F in R to figure out what those critical values Z star would be. So let me show you how we do this. Let's find the critical values for each confidence level. If I want 90%, then that means 0.90 in the middle. And then that means alpha would equal 0.10. Okay, that's how much you have in both tails. Okay, or you'd have 0.05 in each tail. So you have 0.90 in the middle, 0.05 over here, 0.05 in the left tail. So I'm looking for what Z star value would break it up in this way. So we have 0.9 in the middle. So I could do this a few different ways. I could do Q norm. I can say my left tail here has 0.05. So if I do Q norm of 0.05, let's go to R. So if I run Q norm of 0.05, that tells me it's negative 1.6. We're going to round to negative 1.65 or negative 1.64. So we get negative 1.645. So that tells me this value right here is negative 1.645. Now I could say with symmetry that my Z star value I want is 1.645 because we always pick the positive value. And I know if that's negative 1.645, then this has to be a positive 1.645. But I could also type in Q norm of 0.05 and do my lower dot tail equals false. Now this is all based on our standard normal distribution, which is the default in R. So that's why I'm not having to say what's my mean, what's my standard deviation. We know that we want to use a standard normal curve, and that's the default. Okay, so if I put this into R and I look for the right tail with this lower dot tail equals false, it tells me that it's positive 1.645. So we get positive 1.645. So either way, our critical value, Z star, is going to be 1.645. So that's how many standard errors I have to go to get 90% confidence. If I want 95%, we did this one once already. We'd want 0.95 in the middle. I'd say alpha equals 0.05. That's the area in both tails. And so that means we'd have 0.025 area in either tail. So I just divide that by 2. 0.05 by 2 gives me 0.025. So I'll look up Q norm of 0.025. And if I put that in, I'm going to get negative 1.96. So that would be this value is negative 1.96. which means that my positive value has to be positive 1.96. So we'll say Z star equals 1.96. And if I want 99%, I drop 0.99 in the middle. That's going to give me alpha equals 0.01. That's the area left in both tails. And that would give me 0.005 for each individual tail if I divide it by 2. So I'll look up Q norm of 0.005, and that gives me negative 2.576. So this value is negative 2.576, which means the other value has to be positive 2.576. So I can say my critical value, Z star, equals 2.576. Now, my critical values are often written as Z with a little subscript of alpha over 2, because we had to do 0.01 divided by 2 to see that there was 0.005 area in each tail. So that means what's the Z value from the standard normal curve that has an alpha over 2 area to the right? So if you wanted a 95% confidence interval, you're technically looking for a Z value of 0.025, because that's how much area was in the right. But students tend to get confused about the notation, or they tend to just look at formulas and try and memorize the formulas and not understand what's happening. I like to just say it's Z star and draw a picture every time. So we're going to call them the critical values Z star. Okay, now let's talk about our general form for confidence intervals. Every confidence interval can be written in this form. For our estimate plus or minus a critical value times the standard error of the estimate. So the critical value is how many standard errors from the estimate you have to go to get the confidence level that you actually want. You can also write a confidence interval as your estimate plus or minus the margin of error. So the margin of error is this entire part right here. So that's your margin of error. That's the part that you're adding and subtracting. It's our way of saying how much our estimate is probably off by. Now that we have our general formula for confidence intervals, let's see what that would be for proportions. So our general formula of our estimate plus or minus a critical value times the standard error can be simplified to this for a proportion. We'll do P hat as our estimate plus or minus Z star, which is our critical value, times the standard error of P hat, where the standard error of P hat is the square root of P hat times 1 minus P hat over n. So we have this entire formula that we can use every time, or if we've already calculated the standard error, we can just plug that in instead of calculating it again. Now, our formula for our confidence interval is only valid if it's a random sample, and we need to check that our sample size is big enough. We're going to say it's big enough if n times p is at least 10 and n times 1 minus p is at least 10. Some textbooks say 5. In this class, we're going to use 10. That's a more commonly accepted rule of thumb. So in our first example, we have a study published in Medicine and Science. They thought that respiratory issues in athletes are attributed to exercise-induced asthma that may actually be explained by obstruction of the larynx, a different condition. So in a sample of 88 athletes, so let's write down there, my sample size sounds like it's going to be 88. 31 had this ILO condition. So let's calculate our sample proportion would be 31 out of 88, which is 0.352. Now let's find a 95% confidence interval for the true proportion of all athletes instead of just the ones that were in the study who would be found to have ILO under these conditions. Now, notice it did say a sample of 80 athletes. It didn't specifically say that it's a random sample. We'll go ahead and assume the examples given to us are usually random samples unless I tell you otherwise. But it does need to be a random sample for this to be a truly valid confidence interval. So to find my confidence interval, I know that it's going to be p hat plus or minus some critical value that gives me the right number of standard errors away from my estimate, times the standard error, which is the square root of p hat times 1 minus p hat all over n. I like to write out formulas every time. That helps me memorize the formulas. So let's go see what Z star would have to be. We want a 95% confidence interval, so 0.95 in the middle, and I'm looking for this Z value that makes that happen. So how many standard errors away do I have to be to have 95% in the middle? So I'm going to say if there's 95% in the middle, then there's 0.025 0.25 in each tail, okay? Because there's 0.05 in both tails, which means if I divide that by 2, I get 0.025 in either tail. So in R, I'm going to say I need to figure out what has 0.025 area in the right tail. So I'm going to do P norm. Nope, sorry, I'm going to do Q norm because I want to look up that quantile. Q norm of 0.025, and I need to say lower dot tail equals false, or a capital F, because I only want the area to the right, which gives me 1.96. So this Z value right here is 1.96. This one, if you looked up, if you just entered Q norm of 0.025, you would have gotten the negative 1.96. And you could have said by symmetry, then this value would have to be positive 1.96. It's a little bit less typing. So I'm going to say that Z star equals 1.96. And remember, if you wanted to use the official notation, you could say, right, as a Z of 0.025, meaning you had 0.025 area in the right, is equal to 1.96. I just like the Z star notation because I like you guys to use logic and not just memorize formulas. So P hat is 0.352 plus or minus, now Z star is 1.96, times my standard error, which we haven't calculated yet. So let's say P hat is 0.352 times 1 minus 0.352 all over my sample size of 88. So that should, let me simplify that, that should be 0.352 plus or minus 1.96 times 0.051. And let's see, that 1.96 times 0.0 gives me 0.09996. So this is going to be 0.352 plus or minus 0.09996. And so now I'm going to do 0.352 minus 0.0999996. So I get 0.252 to 0.452. So that's my confidence interval. I could say something like, we are 95% confident that the true proportion of all athletes that have ILO is between 0.25 and 0.452. So let's go ahead and write that. So again, this says we are 95% confident that the true proportion of, and we could add this keyword here of all athletes that think they have asthma that actually have ILO is between 0.252 and 0.452. Now, what was our margin of error? Remember, the margin of error is the part that you add and subtract, is how much you think you're probably off by. So you just go back up to your calculations and see how much were you adding and subtracting. So in our case, our margin of error was 0.0996. So that's how much we were probably off by when we made our estimate. Okay, in our next example, this happened in a previous class I did where we wanted to estimate the percentage of Earth that is land. Every group took a sample of 20 points on Earth and calculated the percentage of points that were land. One group got land on 7 out of 20 tosses. So what was their percentage? Their percentage was 7 out of 20 times 100%, which gave them 35%. Now, was this a population parameter or sample statistic? This was a sample statistic because they only took 20 points instead of all the points on Earth. So let's calculate a 90% confidence interval for the percentage of land. So we know it's going to be P hat plus or minus Z star times the standard error. And the standard error is the square root of P hat times 1 minus P hat all over my sample size n. So before I can do anything, I need to find Z star. So I draw a picture. I say I want 90% in the middle, so 0.90 in the middle. So that means both tails is going to be 0.10. So that means each tail is going to be 0.05. Sorry, No, it's 0.05. I was thinking of the 99% out of habit. So we have 0.05 in each tail. Okay, so I'm looking for what Z value would break up the standard normal curve that way. So I'm going to look up Q norm of 0.05, and I'm going to say I want that in my right tail. So my lower dot tail equals false. And this should give me 1.645. So my critical value, Z star, is equal to 1.645. come back over here and plug everything in. So p hat is going to be 0.35 plus or minus my z-value of 1.645 times the standard error, which we haven't calculated yet. So it's the square root of 0.35 times 1 minus 0.35, all divided by my sample size of 20. So this should give me 0.35 plus or minus 0.175. So I'll do the subtraction first. I do 0.35 minus 0.175. That gives me 0.175, and now I do the addition instead, and I get 0.525. So that's my 90% confidence interval. So I would say something like, I am 90% confident that the true proportion of percentage on land is between 0.175 and 0.525. Or we can say, we are 90% confident that the true percentage of land is between 17.5% and 52.5%. Now, what is the margin of error? What's the point that I'm adding and subtracting? So just come back up to your calculations. I was adding and subtracting 0.175. So we realized that with such a small sample size, that when we make an estimate, we're probably off by as much as 17.5%. Now, is there any way to know if this group's confidence interval actually covers the true percentage of land? So to answer that question, let's do some more background theory. So in this class, I had several groups that did the globe tossing activity. We ended up with 20 different results, and we have 20 different confidence intervals. And it's just a coincidence the sample size was also 20. I apologize for that. So here's the number of times that they got land. So then I calculate that to here's the percentage of land that they each got. So here's the different percentages of land. Here's the standard error. These are all written as percentages, not proportions. And you can see the confidence intervals. So one group said that they're 90% confident that the true percentage is between 17.3 and 52.7. Whereas another group, they got a sample percentage of 30. And they said they're 90% confident that the true percentage of land is between 13.2 and 46.8%. Whereas another group got 55% land when they tried it. And so they're estimating that the true percentage of land is between 36.7 and 73.3%. So you can see that every different group got a different confidence interval. So as we go through, did each group get the same number of land results? Well, no. And so they all got different percentages of land, and they all got different confidence intervals. Now, scientists have discovered that the percentage of land is really 29.2%. So is that a parameter or a statistic? That's a parameter because it's for the entire Earth. They actually did the entire population of all of the possible places on Earth. So when we look at it, did all of our confidence intervals contain the true percentage of 29.2%? If you scroll back up and look at them, like this one, yes, this contains 29.2%. But as I go down, most of them contain 29.2%, but this one right here, this does not contain 29.2%. So they happen to accidentally get a sample proportion that was so high that their confidence interval isn't accurate. And there's this one right here as well. It went from 53.2 to 86.8, so this does not contain 29.2%. And as we come back down here, I actually graphed all the different confidence intervals for you. Okay. And I made them black if they contained the true value of 29.2%. And you can see there are 3 confidence intervals that did not contain the true percentage of land. Oh, so 3 did not, and 17 did contain it. So 17 divided by 20 gives me 85%. So about 85% of the confidence intervals that we found actually contained the true percentage of land. So then I went through and simulated some different confidence intervals. So here's 150 different confidence intervals. You can see they're green if they actually contained the true parameter of 29.2%. But you can see that sometimes we just happen to get a sample proportion or a percentage that was so far away from the true population parameter 0.9. So that means 90% of all of our confidence intervals actually contain the true population percentage of 29.2%. So why do you think we say it's a 90% confidence interval? It's because 90% of all the confidence intervals actually contain the true population percentage. Now, is there any way to know if our confidence interval actually contains the true value? Okay. As you come back up and look at all these possible intervals that we could have gotten, I don't know if my sample proportion, if I don't know the true value of 29.2%, I don't know if I happen to get one of these sample proportions, like this one or this one, that were so close to my population proportion that my confidence interval is accurate. Okay. Or did I happen to get unlucky and happen to get a sample proportion that was so far away that my confidence interval doesn't actually contain the true value? There is absolutely no way to tell if I had one of those 90% good intervals or one of those 10% of bad intervals. So let's go up and write that answer. So is there any way to know if this group's confidence interval actually contains the true percentage of land? No. Sadly, there is not. We know that 90% of the time, our interval will be accurate, but 10% of the time, it's not going to be accurate. And there's no way to know if ours is one of those good ones or one of the bad ones.